Well, welcome back, calculus lovers. So we're going to continue our work with the definition of the definite integral today. We're going to take a very detailed look at evaluating an integral by going through the limit of the Riemann sums. So then, well, you might be asked to do on an exam, or at least parts of this, and certainly comes up in the MyMathLab homework. Then we'll also see how we can use the definite integral to take problems we can solve by other means and convert the solutions to integrals. Particularly, we're going to look at the problem of finding the average of a function. So as our first example, let's use the definition of the definite integral to evaluate the integral from 1 to 4 of 2x squared plus 3 dx. We'll use a Riemann sum with n equal with rectangles, and we'll use right endpoints as the representative points, that is the ck's. Then we'll let n approach infinity, which will be our way of letting the mesh of the partition go to 0. So when you face a problem like this and have to use or want to use the definition of the definite integral, that is the Riemann sum approach, there's 5 steps you go through. The first step, and probably the most important, is to construct the partition of your interval, in this case 1 to 4. We're going to cut it into n equal length intervals. So our interval has length of 4 minus 1 or 3. That's how long it is from 1 to 4. So if we cut it into n equal pieces, each of these pieces will have length 3 over n. So here's what the picture of this might look like. So there's a lot of writing here, but again, you really have to understand what these partition points look like if you're going to continue with the function. So here is the 1, the left endpoint, and so our x0, the first number in our partition, is going to be this left endpoint. Now, we've written this in kind of a funny way. We'll see why we want to write 1 as 1 plus 0 times 3 over n in just a moment. Now, if each of these intervals has length 3 over n, as we decided, then if the first partition point after the 0th one, the x sub 1, will have to be 3n to the right. So from 1, I add 3n, and that gets me to this point. And so this first partition point has coordinates 1 plus 3n, 3 over n, but I've written this as 1 plus 1 times 3 over n. I now move 3n to the right again. This is my second interval. It has the same length of 3 over n. And if I add 3 over n again to move to the right by that much, I'm now at the point 1 plus 2 times 3 over n. And after that is 1 plus 3 times 3 over n. So I've put the 1 and the 0 in these two places just to kind of solidify the pattern we're seeing here of the various 1, 2s, and 3s multiplying the 3 over n. Now, I always like to put in the generic interval here too. So here is another interval of length 3 over n. And if this is the kth interval, then just kind of looking at the pattern here, first interval, second interval, third interval, I figure the right endpoint down here must be 1 plus k times 3 over n. That's because the 1 plus 3 times 3 over n is the right endpoint of the third interval, etc. So I'm just taking that pattern. And so the one before it must have been 1 plus k minus 1 times 3 over n. Finally, if I'm making n intervals, the last one down here also has length 3 over n, and its right endpoint is going to be 1 plus n times 3 over n. So this is for the nth or the last interval. And of course, 1 plus n times 3 over n is equal to 4, and that's good because we should be at the point 4 by the time we get to the end of that subdivision. So I've recorded those coordinates here, and then down here, of course, we would, in our Riemann sum business, call these x0 for the left endpoint, x1 for the first, x2 for the second. Here's xk minus 1 goes right there. The xk point is here, and the xn point, or 4, is the last one there. Now remember also we have a length for each of these intervals. As we know, it's 3 over n, but notice that we get that length also by computing the difference of two consecutive points. For example, if we do xk minus xk minus 1, it's easy to see that that difference does turn out to be 3 over n. So the delta x's, that is our interval widths, are 3 over n in this case. So as I said, this is probably the most confusing and meticulous, but probably important of the steps we're going to go through. Now, once we've got our partition points, we move on to step 2. Okay. So we're now going to draw the rectangles using left endpoints as representative points to determine the heights of the rectangles. We're going to let f of x equal 2x cubed plus 3 because that's the function we want to integrate. And we'll use that notation, the f of x, just to save a little bit of writing. So we go back to the picture we just finished and we look at the left endpoint of the first interval, which went from x0 to x1. Of course, that's going to be x1. And so that height of that rectangle will be f of x1, the height to the graph. The left endpoint for the second interval, which goes from x1 to x2, these should be right endpoints. We were told to use right endpoints. I apologize. I got the points right, but I just didn't write the right number here. So these are all right endpoints. Okay, so we'll go ahead with that correction. So the right endpoint of the kth interval is x sub k, so the kth rectangle has height f of xk. And find the right endpoint of the last or nth interval, which goes from xn minus 1 to xn, is going to be xn, so that last rectangle has height x sub n. So here is a sketch of a few of those rectangles. Again, I want to get rid of all these lefts and make them rights. But other than that, it is perfect. Okay, so here are what the rectangles look like. I drew in the second rectangle down here with its height appended next to it. So there's the second rectangle, and its height is given by f of x2 because that little point down here is x sub 2. Okay. I haven't written in the one for x1 because there's not space. Here's the generic kth rectangle over here. This right endpoint here would be x sub k, and its height then is given by the function value at that point, fxk, height given by fxn. Now, really, if you know the sum formula for the Riemann sums, the definite integral, etc., you don't really have to draw this picture, but I always find it very helpful. And we're going to continue with this area rectangle analogy as we go through the problem. So, we now can compute the areas of all these rectangles just by multiplying width times height. So for this first rectangle over here, there's rectangle 1. It'll have height f of x and length, width, which we call delta x1. But of course, these all have the same width, 3 over n, and the height, of course, is still fx1. So this first calculation gives us the area of the first little rectangle down here. And that trend just continues. Again, let's look at the generic one. The kth one is always of interest. The area of the kth rectangle, again, is just its height, fxk, times its width, delta xk. The widths are all 3 over n. That was instructed in the problem. And then width times height. Okay. So that completes step 2. You want to write out these rectangles, draw them if you have to, and then be very careful about understanding what the height of each one is and what you multiply together to get the area of each of these rectangles. Now, once we have this in place, step 3 is to form the Riemann sum for this partition. So you can think of this as summing the areas of the rectangles. So the sum is just the sum of area rectangle 1 plus area rectangle 2, etc. We've already figured that out. We saw earlier that was fx1 times delta x1, fx2, delta x2, and so forth. And we can write that in summation notation by taking the summation as k runs from 1 to n, fxk, delta xk. This is why I like to focus on that generic kth term, because if you really understand that, that is all you have to put in the sum. And then when you let k run from 1 to n, the k equals 1 gives the first term, k equals 2 delivers the second, and so forth. So understanding the generic term is important if you want to use the summation notation. Now, step 4, now that we have arrived at the Riemann sum, we're now going to put in our expressions for the x sub k's and for the function f, and use the fact that all of our intervals have the same width. The delta xk's are all equal to 3 over n. So this sum, which you just recorded there, is going to look like this. So I've done this in 2 steps. We first of all put in the 3 over n for the delta xk's, and the f, remember, takes whatever is in parentheses, squares it, multiplies by 2, and then adds 3. And so we want to do that to the x sub k, which is in the parentheses in the sum. Then, of course, we took great care mapping out what those x sub k's are. And so x sub k, I know x sub k is given by this. So the 2x sub k squared becomes twice 1 plus k times 3 over n squared plus 3. Okay. Now, when you work through these problems on your own, try not to skip steps. Write out all these steps. If you skip steps, chances are you're going to make a mistake or leave something out. And from here on in, it is pretty much just algebra. So, all we did in the next step, we did a little bit of algebra, which involved expanding this square. So when I squared that out, I got this expression down here, 1 squared. And then when I square the 3k over n back here, I get k squared 3 over n squared. And then the cross product term, the middle of the FOIL term in that square, gives me 2 of the k over 3n terms. And then here's the plus 3 and the 3 over n still recorded there. Now a little more algebra. I have a 2 times 1 plus 3 is 5. So I collect those to a 5, and I'm going to bring that 3n inside and multiply it now by each of the terms that we're adding together there. Next, we have a 2 times 2k. That gives us 4k. I have a 3 over n here, and that's multiplied by this 3 over n outside, this 3 over n outside, and that's where the 3 over n squared comes from. And then finally, the last term, I have the twice k squared. That comes there, and 3 over n squared times another 3 over n gives us the 3 over n cubed. Now, notice here, and this is advice to you, don't be in a big hurry to necessarily multiply everything out and simplify it. I've kind of kept things expanded with 3 over n's, just call them squares, cubes, etc. I haven't put those together yet. I may in the future. Likewise, you know, this k 3 over n business, keeping those separated was and will be important, because I want to focus on these k and k squared terms. But this step was just algebra, expanding and then doing some multiplication with the distributive law, distributing the 3 over n inside the multiplied term, the expanded terms. Now we're going to take that last expression, which I've recopied here, and split it into 3 individual sums. This is just a form of the commutative law. And at the same time, I'm going to pull out in front of the sums everything that doesn't have a k in it. So for this first piece, we have 15 over n There's no k's in that, so I'm going to factor that 15 over n out in front. What's left inside the sum is 1. So that first piece gives us 15 over n times the summation k runs from 1 to n of 1. What that means is we're adding up a lot of 1's, n of them. The next term we had 3 squared gives 9 times 4 is 36. So the 36 comes out in front. Likewise, the n squared down here doesn't involve k, so I factor it out of the sum too, because it's not going to change as k runs from 1 to n. And then the last term, 2 times 3 cubed is 54, and the n cubed comes out in front. Now in section 5.1 and 5.2, you saw these kinds of sums. And in fact, if you look on page 309 of your book, you have formulas for the second and third sums there. That is, what do you get when you add up the first n integers, 1 plus 2 plus 3 plus 4 and up to n, and the first n squares, 1 squared plus 2 squared plus 3 squared, etc. on up to n squared. So I've looked those up in the book and recorded them down in the next line of equations below. And then as far as this first sum is concerned, as we mentioned, we're just adding up a bunch of 1's, mainly 1n times, and so that sum has value n. So our work continues down here. We have the 15 over n out in front times n, then 36 over n squared, and now again I just went to the book and looked up that sum. It comes out to be n times n plus 1 over 2. And the same page in the book gave us this sum, a little more complicated, but still just a polynomial, n times n plus 1 times 2n plus 1 over 6. So now it's just a bunch of algebra. 15 over n times n gave us the 15 out here. In this next term, I just expanded the polynomial in the top to get n squared times n to get n squared plus n. 36 over 2 gave 18. So this expression simplifies to that, and likewise I just did the expansion and cancellation on the third degree term over here to get this term. Now finally I split each of these things into fractions. I get 2 fractions with the denominator n squared out of this one, and 3 fractions with the denominator n cubed out of this one. And there's the result of doing the second term, here's the result of doing the third expression, and of course the 15 stays out in front. And then finally combine like terms. So here then is the result of our Riemann sum, n equal spaced rectangles for the interval from 1 to 4 applied to the function f of x equals 2x squared plus 3. And when I do the sum of the areas of all those rectangles, this is what it boils down to. Amazingly simple, although it has been a lot of work. Now, the last stage, okay, is to take the limit as n approaches infinity. Okay? So when we do this, the 3 over n goes to 0, and of course what that really means is the partition is, the norm of the partition is going to 0. Since all these intervals have length 3 over n, when n goes to infinity, 3 over n goes to 0, the norm of that partition is going to 0. So we'll finish off by doing this last step. So according to the definition of the definite integral, the integral is by definition the limit of these Riemann sums. We just finished evaluating at least a special case of those Riemann sums here. And it's pretty easy to see what happens to that when we let n go to infinity. The answer is 51 for this integral. So again, these are long, tedious problems. It would be too much on an exam to have you do one of these from start to finish, but you should certainly be able to work with intermediate pieces, work with the sums, talk about what are the partition points, the CNs, etc. Maybe come up with the areas of 1 or 2 of the rectangles. So know this process well, practice it, do the MyMathLab homework that goes with it so that you're very familiar with all the pieces here. So this shows how we can use Riemann sums to evaluate integrals if we need to. It turns out there are many integrals that we cannot do by any easy method, And if you run across functions that are of that nature and have to integrate them, you'll probably have to resort to something like Riemann integrals, of course with the help of a calculator or computer. Now, we can also pass the other way. We'll often pass from a Riemann sum to an integral, and we're going to show one demonstration of that, and that's the calculation of the average value of a function over an interval. So in section 5.1, we talked about the idea of estimating the average value of a function. We did this by evaluating the function at several equally spaced points and then finding the average of the function values at those points. We took maybe 3 or 4 equally spaced points or 10, added them up, divided by 3 or 4, 10, whatever is right, and that seems like a reasonable way to average a function. Now, we can actually now extend this process with the help of the definite integral. So let's imagine we have a function defined in an interval AB, and we want to find the average of f at n equally spaced points in the interval. So again, we have this equally spaced, which means we're going to be thinking of a partition into n equal points. Now, this is very much like the last problem, except we're not going to work with a definite f. But here, our interval, we find its length as b minus a. You always get the length of interval by subtracting the smaller value from the larger. We want to divide this interval into n equal pieces, so each of those pieces is going to be of length delta x equals b minus a divided by n. So here's what the partition might look like. Okay. So this is the same picture we had last time, except instead of 3, we have b minus a, which was the 3 in the last case. And we have a instead of 1 because this integral starts at a rather than 1. So again, each of these intervals between here is the same length, b minus a over n. And so to get from one spot to the next, we always just add one more b minus a over n to it. So study this picture, pause the video if you like, kind of convince yourself this looks good. And notice we have the generic ones in here too. Here is the kth interval, and its right endpoint, again looking at the pattern back here, is a plus k b minus a over n's. The last one, the nth endpoint, should end up at b, and sure enough, a plus n times the quantity b minus a over n is equal to b. So again, we've done pretty much the same thing we did in the previous example, but just in a little more abstraction. So these are our equally spaced points, and we're going to evaluate the function at n of these points, the first, the second, the third, etc., on to the last one. That'll be n function evaluations, then we'll average those n evaluations to get the average value of the function. So there's that calculation we just alluded to. Find the function value at each of x1, x2, x3, etc. Add those n values up, divide by n. And if we want, of course, we can write that in summation notation as 1 over n times the sum k runs from 1 to n, f of xk. Now we do something a little tricky. We're going to multiply and divide this sum by b minus a. So I'm going to multiply by b minus a over b minus a. The bottom b minus a I'm going to leave out in front of the sum. The top one we're going to put over the n and bring inside the sum like that. And I like seeing b minus a over n because that is the delta x. That's the interval length in this problem. So this average of n things can be written as 1 over b minus a times the sum k runs from 1 to n of f of xk delta xk, where of course the delta xk is b minus a over n. Now, if we decide we can get a better reading on the average by taking more points, well, let's see what happens when we let n go to infinity. So if I take the limit as n goes to infinity of all this stuff here, here's the limit of the average, and of course we can do that by putting a limit in front of this sum over here. Now, this last sum, this last limit is important because this looks like the limit of a Riemann sum, i.e. an integral. Because remember, the definite integral is defined as the limit of Riemann sums. So, because this sum arose from partition the integral from a to b, we know that this defines an integral from a to b, and we have the following. In fact, this is how we will define the average of a function over an interval. It is 1 over b minus a times the limit of the Riemann sum. And now by the definition of Riemann sum, but rather by the definition of definite integral, that limit is by definition this integral. Okay. So again, the integral and the sum are the same thing. They mean the same thing, but of course this notation is a little simpler, and it's what we're going to be working with in the future. So this is an example of how you might try to solve a problem and your solution leads to a Riemann sum. You decide that to make the solution more precise, you make your rectangles or intervals smaller, let n go to infinity, and if you do that, you then see, oh, what I really have here is by definition just a definite integral, and so we can write a result in this way. Okay, in the next videos for section 5.4, we'll look at ways to evaluate definite integrals without going through the bother of partial sums. So sure, we'll all look forward to that. Good night.